Hello, everybody. So today starts module 2 for our class. These 8-week classes do go pretty quick. Got a few things to cover. One, a note about those backups in Raptor. You all may have noticed that. I was going to talk about that whenever we get to that. What I had in mind today has 2 Raptor examples, sort of small starting out things. One that's not covered in the statewide module and something I always like to talk about because I think it's very useful and helpful, but we will get there very soon. And then a second one that's a simple example that I think everybody can relate to. What I chose for this time was a tip calculator. That's a common thing that I think everybody in America is at least vaguely familiar with, how to calculate a tip after when you go buy a nice meal. So we'll look at that just to practice with math and doing some stuff. Essentially similar things to what that video was covering. Talk about some stuff. One thing I was thinking before this semester started, every time I've run this class, I let people choose the projects. At the end, we have a final project, and the statewide course shell always has instructions to do this one explicitly. And I've always just let people choose the projects, and I was thinking, well, maybe I'll go with that same one. And then after reading the intro discussion boards, I started to doubt that decision because everybody has different interests, right? So some common things I see, one that I saw all over the discussion board was gamers. And that is a great way to practice these concepts. If you can move those images around and make them interact with each other, you understand how to put an algorithm together, the little step-by-step process. And it's a lot of fun. I know when I develop games, I find that's I have as much fun as playing them. It's like a riddle or a puzzle in itself. So I want to put that option back in. A number of cybersecurity people. So one category project I've seen shown up a lot over the years, especially as cybersecurity has become more and more popular, is write small encryption things. Obviously nothing that would compare to the modern, super complicated ones that we use, but at least the basic idea of encryption. Come up with an algorithm that would be kind of hard to crack with some keys and hide the data in such a way that you can still recover the data. Because encryption is very different than just mixing up the data, right? If we just mixed up all those bits to where somebody couldn't read it, it's no good if we can't get it back either. So it has to be hidden in certain ways so that it can still be recovered. Which addresses a question that was asked the other day. Is there a cryptography class? And I hadn't encountered one before, so I asked Kenyatta. He's the chair for the cybersecurity program here at Sellersburg. I went to the course curriculum and searched for cryptography, thinking it would at least show up in course descriptions or something, but Control F didn't find anything on that page, nor did the regular search box. So I asked him, and he said there's a class called CSIA 245, which is getting renamed at some point soon. It's going to be SDEV 245, that is cryptography. And when I brought it up, he also he immediately said we should probably teach this here at Sellersburg. So I think it was you that asked that question, Tyler. Do you still have?
Yes, indeed. Yep.
Are you still in a class with Kenyatta?
Yeah, I was with them earlier today from 9 to 11.
Okay, so he would be the one that would schedule that. So if you can maybe talk some other cybersecurity people into that and have at least 2 students that want to take that. Sure. That would be a nice way. Once there's 2 or 3 students that definitely want to take that class, that would be a good way to make sure he gets that put on the schedule.
All right, I'll try to gather an interest list. Thank you.
Yes, because you're not the only one interested in that. So it's
really cool. Anybody who likes Gravity Falls would love the class. Come on.
Yeah.
There's a cryptology puzzle at the end of every episode. It's great.
Yeah, it sounds like an interesting class, and that's one that's very popular for a final project. So I decided, well, instead of doing that statewide one where everybody does the same thing, I think it's like a gym membership this time around. It changes every 2 or 3 semesters they change it. I think it's a gym membership thing right now. It's like, I'm gonna let people pick their own final project. something that'll have to be approved, so I'll get those instructions in there. And speaking of instructions, I noticed something on those Raptor assignments. I had changed some instructions to some general homework submission instructions to the way I always do things. And apparently I didn't hit the save button. So those Raptor assignments, there'll be a slight change to what they are. The biggest one is some of the alternative formats. There was a long list of things, and some of the alternatives weren't as good as others. Here at the beginning, drawing a picture or simple pseudocode works really well. But when we get near the end, as things get more complicated, if you're drawing a picture and can't run it like the Raptor or Flowgorithm or one of the Flowcharts or Blockly or some sort of graphical thing that you can actually run the code of and confirm that picture, it's easy to miss things in the pictures. So I usually try to avoid those, but I apparently forgot to hit save. And then the big change there, because if you just really want to do the drawing thing, you could probably easily convince me to do it to let you do it that way, because that is our standard of international communication in IT, is a pictorial based language. So drawing our knowledge instead of writing words is a standard, in a worldwide standard in IT we want to get familiar with. It's called Unified Modeling Language, and we're going to talk about it throughout the semester. But the big assignment that'll affect all of them, no matter which format you choose to turn it in with, is I like to ask for a bug report, which is a simple write-up. It doesn't even have to be grammatically correct. It can just be random notes jotted down in the comments that tell me how it went, how the development went. What problems did you encounter? What did you do to fix those? And it applies that basic learning tendency of reflection, right? We preview, learn, reflect, and that's how that helps to reinforce the knowledge. So writing down what went wrong and what you did to fix it helps with that. It also helps me to know when there's like a broad list of things that need recovered or covered in more depth. So that was a couple of the announcements. So on the not the textbook assignments, but the programming assignments for here, where you can do Raptor or draw a flowchart, that's one of the options I was going to remove. But if the people who wanted to do that really want to do that, let me know. We'll talk about it, just because when we can't confirm the pictures at this level, that can be a little bit confusing. But on the other hand, if you've had IT stuff or like computer science stuff in high school and know that stuff and want to practice it for the purposes of learning, getting better with unified modeling language, then that is a very good thing. So it wouldn't take much to convince me to let you do that if you just want to do the pictures as their own separate thing. So that's a few of the things to go over today. Couple examples to get started working and stuff. And this is an active subject we learn by doing, but there's still concepts involved. We want to talk about the concepts. So does anybody have any questions before I go over to the board and start writing some stuff there for the notes?
Nope, I'm good.
Okay, I assume, yeah, silence usually means no questions. So our main thing we want to look at today is something we actually looked at that very first day. We're just going to talk about it in a little more detail. I figure y'all were anxious to get started. I always like to get started right away. So memory and output. Seems like a good starting point, because that's why we did that first discussion board, that program thing. So every program we need, well, when we're programming, we're working in RAM. So we're going to be using memory, but we need to set up variables and work with our data in RAM. And every program we write is probably going to output something. That's generally the point of writing the program, so we get the output of it. And we started looking at this, and I drew this picture, and I want to leave this picture on the board for now, what I called our general picture for the class, our starting point. As we come in here, what I kind of expect everybody is familiar with is that computers take in input and give out output. And in between there, stuff happens. So in this class, we're kind of filling in that stuff happens. So, which we can start filling in now. Which I need a little bit more room there. I'm going to make that bigger. Sorry. Make that a little bit bigger. Is our intro discussion board. I'm just going to do a simple line referring to that to help make this picture make sense. Because we took it a step. Took our first step further than just that stuff happens in there. We set up some variables. So I'm going to use mine. So there was like a name variable where I stored my name in there. Then I set up an age variable and stuck my age in there. And then another box right over by the output, concatenated those together. So like name plus the words is plus age, and then we did the output. And these pictures I drew on the board here, I'll make this in a little square. You probably noticed those are the same pictures Raptor was using, the rectangles and the parallelograms. And that is part of our international standard pictorial language, unified modeling language, or usually UML is how we abbreviate it. We're going to talk about it in detail soon, but yes, preview on it. That is the standard image to represent volatile storage or memory, where we store variables or when we do some processing. In this case, concatenate together these strings. That's a type of processing. So that happens in our random access memory. Then our input and output are represented by parallelograms. So we stored our data, concatenated it together. We did it, I think it is out right in the output box there, but we could very easily just have done all of that and stored that to another reference name and then output only that reference name. So like did the whole concatenating the message, stuck that in a variable, and then just output that variable because it held all of that stuff. So we can split it up in more than one way. But there's a subtlety there that we as intelligent creatures took for granted. The order these things happen in really matters, right? We can't do the concatenation first. We have to have our data there before we concatenate those data points into an output sentence. So the order these things happen in really mattered. In our case here, the 1, 2, I'm going to write 3 and 4, just to kind of split it up, get 4 things in there. I think we did it as 3 steps in our example the other day. But the order matters. We take that for granted as intelligent creatures, and what we're studying in this class is kind of summed up nicely in that point right there. Nothing can be taken for granted when feeding instructions into a machine. Every step of the algorithm must be explicitly stated. And so focusing on that thing that we just automatically took for granted and didn't put much thought into it, we're intelligent creatures. We can fill in gaps. We can fill in the background stuff. Kind of like that point I made about why I usually take out the option for just drawing the flow chart and actually using one Raptor or Flowgorithm or something that'll actually run. One of our examples today is going to go over why I prefer Raptor over Flowgorithm. Has to do with its full language, but we'll get there in a moment. We can take stuff for granted. So like drawing out a flow chart, we could leave a part out, and that's the plan for our program. Then when we go write that program, we're going to look at that picture, and we're intelligent. We're going to know that part's missing and go ahead and type it in, say, Python code or something. So we can take stuff for granted that the machine can't. And that's what we're studying here. Leads into our 4 constructs. I started sort of previewing those the other day. And what I wrote for sort of a definition here, when I was redoing my notes, over the last 5 or 6 times I've taught this course, my notes have gotten really, really messy. Like more notes have come and gone, and there's edits and annotations in the margins and all sorts of stuff. So I was redoing the note. I figured it was about time to redo the notes nice and clean. As I was redoing them, to summarize the 4 constructs, it's the type of tools needed to solve any problem. So problem solving in general, and that's a transferable skill beyond IT as well. How do we break down and analyze a problem, assemble a set of tasks that would work to assemble a set of tasks and carry those out in the right order to actually solve that problem? It's back to that point I just made about taking things for granted. As intelligent species, we can do that. We can take things for granted and make adjustments along the way. But and that's fine for easy problems, but not everything we do is an easy problem, right? Sometimes there's hard problems that we get completely lost when we're faced with them. I'm sure everybody's encountered a difficult problem that you just had no idea what to do with, right? Your human intuition of problem solving skills completely failed you and just left you standing there with a blank look on your face at some point in your life. Happens to all of us. So what we're studying in this class can apply to those situations too. Analyze that problem, figure out what steps need to be taken to solve it. What order do you take those steps in, and then address it. It just so happens that that's what we use our machines for, is problem solving. So it's a great way to focus in on that. So the 4 types of tools we need are a sequential tool, a selection tool, reiteration, and an invocation tool is the term that's typically used for this. And by invocation, the key part there is invoke. We're going to use something that's not our own. We're going to step out of our sequence, do something else, and come back to it. Maybe use a pre-existing tool or generalize the tool so that we can use it elsewhere. But we're going to invoke something that's not part of the things we immediately have at hand. And you might notice that those words are slightly different than the list I put up there the other day, because this is a generalized concept thing. So I do intentionally change these. So we want to look at the meaning behind them, not the specific word written there. Right? The meaning, the analysis of what a sequential tool is what matters. The sequence, that's the order. We need something to define the order we're working in. That's the first one. We'll get to the rest of them in sequence, but that's the tools to solve problems. And then when we apply those tools, the step-by-step process for using them, That's an algorithm. So that's what we're studying. So starting with sequential tool here. Let's see. The simple set of tests. So this is problem solving in general, which is a transferable skill beyond IT. We're just using an IT setting to study it. I put a note here: as intelligent creatures, this is often instinctual to us, to the point that we do it without paying any attention whatsoever. Right? Like, y'all register for a class, and this class is a virtual class. So by this point, I think everybody probably knew that was going to be on Zoom. Some of y'all, this might be the first time you've used Zoom. Others have probably used Zoom before, especially for those who've used Zoom before. How much thought did you put into the act of solving the problem of getting to class the first day? Yeah, you probably knew where to look. You went right over to Ivy Learn. I tried to put it on the homepage right there at the top of the homepage, so it was easy to find.
First time I tried to do Zoom, not this semester, but last semester, I tried to use like the Zoom web page, and I was like, oh, you actually have to download it, and then it made me late for class.
Yeah,
Yeah, that type of thing, you know.
Yeah, the little things like that. You tried to do it all on instincts. You kind of knew what to do ahead of time because you've used.
Yeah, and one of my experiences, and this is quite hilarious, is that previous times you use Zoom and everything, and I was clicking to press the link one time, and I just thought, oh man, that's the right link when it was, but it was like, it didn't work, and so like I was just like wondering why, and there was then I emailed, and I just was 10 minutes late, since I pressed the link, but then it's says the host will let you in soon, and that person was not late. So what happened is that I had to go to another link, another Zoom link within the calendar. I had to press the calendar one, since they had a link that they sent me through the inbox. And so like that was the link I used. And so I was like, think nothing of it. So I went to the calendar one, and it finally worked, but I was like 10 minutes late.
Yeah, I've done that before in class. I've gone to log onto a class, like not even first day, like in the middle of the semester. Just gone through the motions and started a Zoom room, and then sat there, and nobody showed up at the time. And then suddenly realized, like, oh wait, this is the room for the Tuesday, Thursday class, not the Monday, Wednesday class.
Yeah,
So everybody's
but it's crazy. It was like a link for the same class for the same date, but it was like, maybe it was like a bad request type of thing. It didn't say that,
Yeah.
but I was like this, but it said
Yeah,
the host.
that's problem solving, right?
Yeah,
That's what we're studying. When you hit that problem, or when you spotted the problem, like something's wrong, you had to break down, figure out what was wrong, then break it down into the steps to fix it. And
yeah,
like you said in your example, Keegan, it was almost instinctual. You checked you knew another spot there was a link, so you checked that one.
yeah. About that,
Machines can't do that.
Yeah, about that, I restarted the same thing until I got to the calendar. So what I did was I just continue.
You got there eventually, though.
Continue, press the same link, didn't work. Continue, press the same link, didn't work.
Yeah.
And so that's when I did the calendar thing. I wasn't
Yeah,
like,
so that's
so I wasn't like, ooh, let me go to the calendar thing. I was kind of like, why won't this open? Why won't I be in?
So that's problem solving. That's what we're studying. We're studying in an IT setting because it's exaggerated in an IT setting because machines cannot take anything for granted.
Yeah, plus
we talked about this the other day. Machines only follow a pattern. So
yeah, do machines like
everything
can machines drive into insanity? Like they try to repeat the same thing over and over, and then it just the system crashes because it tries to complete the same problem over and over again. Like
yes,
like
that is something we're gonna face this semester as well. Something that pretty much always shows up at the introduction level, just about guaranteed. I learned to program about 30 years ago when I was about 9 years old.
Right.
And it still shows up, and that's we forget to tell the computer to stop repeating. When we start repeating things,
Mhm.
that's a trivial point at the end. So we think about the hard steps
Yeah.
and then forget to tell it to stop
And
repeating.
plus that's the definition of insanity, is doing the same thing over and over again, expecting a different result.
But
So
yeah,
that's the same
for-
thing
for
that
a
can happen
human,
with
for
computers.
a machine,
Same
that's
thing that happens
just
with
what
us.
machines do. So there are a few points here. I'm going to step back over to this picture real quick. Actually, I left a spot over here to draw it because I wanted to leave this one up. So this is the general picture I use, sort of that bubble to represent the mysterious thing that we're here learning. There is some standard diagrams we use. So one of our standard diagrams for representing what's going on here is a stack heap diagram. I briefly introduced those the other day. Stack heap. And the general way to think about it is the stack side. Think of this as our code. And heap is RAM, the random access memory. The foreground where we're writing our code and the background. The biggest thing to note on this is there's a definite bottom to the stack. The way these pictures are drawn, the heap's just open at the top and bottom. We're just looking at some spot in the middle of it, but there's a definite start. So to a machine, that's where the sequence comes from. So in programming languages, our sequential tool, the order things happen in, that thing that we just kind of took for granted, that is brought on by a stack of instructions. Computers work in stacks, which it's a last in, first out data structure would be the technical way to say it. Last in, first out, which the standard example is the plates in our cabinet, right? We eat dinner, after dinner, we go wash the dishes, and so we wash the first plate, dry it, put it back in the cabinet. And we wash the second plate, dry it, put it back in the cabinet, and till all the plates are up there. And then when we go to get another one, the last plate to get put away, so the last one in, that's on top of the stack. So that's the first plate we grab the next time we go to eat. So computer instructions work the same way. Literally, like we write them in a text file or flowchart pictures, which actually writes a text file in the background. Raptor actually writes either Perl or Java. We're just going to do the one with Perl this semester, but it actually writes a temporary text file in the background of the same order, the text code in the same order we put our instructions. And then the computer reads those in bottom to top, so that the last thing on it'll read the last line, the second from last line, and so on until it gets up to the first line. So the first instruction we wrote is at the top of the stack, so that's the first instruction to run. So that's where our sequence comes from in tools. So in this case, what we did the other day, first, well, there was 4 steps here. So the very first step is we said create this variable called name, and I'm going to talk about variables in detail on the next page of my notes actually. So what that does is it refers to a spot in memory. So when we said create a spot in memory, we're going to call it name and talk about variables a little more here shortly. And stick, well, in my case, we stuck the name Chris there. Then the second instruction was again create a spot in memory. Call it age, because the computer's going to call it, I don't know, the computer's going to stick it over here and say, okay, here's a spot in memory. So put the number 43 there, and the computer's going to remember it because maybe that the computer remembers it stuck that at bit 187,214 in our RAM chip. Okay. That's no problem for a CPU to keep track of, but we'd never remember that. I already forgot what number I just said. So if there was a whole bunch of things like that, there's no way a human would keep track of it. And I split the last two up. I think we did them as one step in our example the other day, but splitting them up, our third one was to concatenate that, which is processing. So that would get a square box again, because we're doing something and we're still in RAM. We haven't sent it to output yet. So that's going to be, we referred to this thing plus some other words plus this thing. So we referred to those things we already had, added some other ones. So Chris is 43 years old to make that a full sentence, but I definitely ran out of space on the board there. That doesn't look much like an arrow. So this data plus some other words plus this data plus some other words, and then we stuck that at some spot in memory that the computer keeps track of, which is all ones and zeros. I'll write a bunch of binary code there because that's what the computer does. It puts it in the language it knows and sticks it in there. Which I noticed I had an interesting little prop that I could have pulled out the other day. I was looking at putting some stuff back in my electronics box and was like, oh yeah, I forgot I had that. So this is what's called a dip switch. It's just 8 switches. Basically, when we start talking about bytes, that's what a byte of data is. It's 8 switches. This one goes really slow because these are little bitty ones, way too little to use my finger on. I have to actually find something to poke them with. But it's 8 switches. And that's what the ones and zeros are. So like right now, they're all zeros. But if I come through here and say do that, that, and that, now it's 0, 0, 1, 0, 1, 0, 1, 1. And then the electricity gives us speed with that. We let the computer flip its own switch and it can be done billions of times a second. So that's what's meant by binary code, and we're going to cover that in detail in module 3. Then our final instruction was to output that. So our standard, international standard of communication to parallelogram is we're going to take this data and send it out to a user, which for unified modeling language, UML, that's pictorial standards, that is usually just a stick man. So we just use a stick man to represent a human, and we refer to the technical term for that's going to be actor. When we need a human to show where a human interacts with our program, just draw a stick man. So a couple of those symbols, working those pictures, and hopefully you're seeing that they're not complicated pictures that we draw, right? We're not, you don't have to be a master artist to work with that international pictorial language. It's squares and it's rectangles and parallelograms and stickman and little simple things to work with. So that's how it looks. And then our sequence, the actual way the computer runs, is a stack is also a temporary thing, kind of like the stack of plate and stack of plates. When we wash them after dinner, put them back in the cabinet, they're only going to sit in the cabinet until the next meal. It's a temporary holding spot. So our term for taking things off of a stack is we pop them off a stack. So after we put all those instructions in, or we set up the instructions, then we hit run. The computer loaded all those instructions in, and then it starts popping them off one at a time. And that's when they actually run. So after the stack's made, we pop off that first instruction. And at that point, we have this data over in memory. Then once that's done, the computer comes back and pops off the second instruction. Then we have these 2 data points. Then it pops off the third instruction, which can calculate it, did our processing. And then it pops off the fourth instruction, and it's down to the bottom of the stack. It's done running the end of the program. So that's sort of that's the standard picture to represent how computers process. And well, it's volatile memory, meaning temporary. Things go in and out as they're needed. And a stack is a temporary thing. We put our instructions there and then we pop them off the stack. Temporary storage, like when we put dishes in the cabinet. It's only going to sit there until we get hungry again. Then we're going to take that plate back out and eat more food. So that's sort of the standard picture, but I like to use pictures to represent things. Which is the first example the first example to get into. I had some other notes here. Yeah, I'll talk about variables in more detail later, because while we're talking about pictures, that seems like a nice segue to the first example for today, which I originally had at the last page of my notes. So a lot of people like visual representations. Has anybody heard that term visual learner? It's a very, very common one. We learn by seeing something, seeing a nice representation of it. I like to make analogies. You'll hear me make analogies constantly, trying to relate it to other things that you're familiar with. And pictures are a good version of that. So we're using flowchart interpreters for this class. So that we have that picture of how our data flows through the program. And graphic stuff can help with this. So one of the things I like to look at is doing graphics in Raptor. And this is the main reason I always choose, well, Raptor's in the statewide course shell, but I have a little bit of freedom for the classes running at the Sellersburg campus, since it is the statewide asynchronous online version. The reason I didn't switch to Flowgridim is Raptor is a full language, and we can do as a full language, we can do graphics in it. We can handle our graphics. So I thought I like to include that. That's a great place to start with. So basically just drawing a picture is a great way to practice the sequence. So if we open up Raptor, window, tile vertically, something I was going to point out, well, I guess this is a good place, is notice we have different modes that we can run Raptor in, either Novus mode or intermediate mode or object-oriented mode. We won't get to object-oriented this semester, but so you'll want to make sure you're in one of these two, and eventually we'll need intermediate mode because they have different functionality. We need at least Novus mode for today's example, because we can draw a picture, which actually kind of jumps up the list to our fourth construct there, the invocation. We're going to invoke something that already exists. And for that is Raptor used this symbol, that call box. It's like a square to represent the similarity to our rectangles that mean we're doing something, either storing or processing. But they added this big arrow on it. That's a little different than our UML symbol. The official UML symbol for call is a rectangle with double bars down the side. So if you're staring at big complicated pictures for a long period of time, you can probably see that start to blur together into the other one. So we're allowed some customization, right? If we just add a big arrow on the side of that, it's still quite clear which one we're talking about. So Raptor went with a little bit of customization to make it a little clearer what that symbol was representing instead of the official one. All the other symbols they use are the official standards. We can call pre-built code. The one we want to call here Well, it's one of our examples there, open graph window. And the call box tab does work. So when it shows up in the little box at the bottom, if it's red, you can use up and down if there's more than one thing to, and the one that's red, if you hit tab, it'll fill that in. So open a graph window. It's graph like in math class, the XY coordinates, which that's what builds up to graphics. That's how our screens work, is the XY coordinates like you're used to from math class. The x-axis goes horizontally and the y-axis goes vertically. And then every point on there gets a new a 2-value reference, an x and a y coordinate, say which one it is. So all of our pixels are like that. Generally on a screen, the x-axis is positive to the right and the y-axis is positive going down. I've heard 2 explanations for that, both of which make sense, but I've never been able to narrow it down to the absolute confirmation. And one, because the people that made those choices, I don't think they're probably not even alive anymore. That was a long time ago, but when the screens were created, it was around the time NASA was doing simulations on the Apollo missions. So one of the explanations is that when they were doing their simulations and they wanted the picture of it, gravity pulls downward. So it's very, very common in physics class to adjust and make our y-axis go down, because then gravity becomes a positive number and we don't have negative numbers everywhere. The other explanation is like lines on a page. Line 1's at the top, then line 2, line 3, line 4. Both of them make sense, but you'd have to actually ask the person that decided that should be the standard to know for certain. And if you go around looking on Google, you'll find both explanations, or you go to research it, you'll come across both explanations. I think it probably has to do with lines on a page, is what I've always thought was probably the more likely one. But again, both stories are out there, so the only way to confirm it would be to find the person who made that decision and ask them. But we have to say how big of a screen we want to draw in. So maybe width of, I don't know, 765 pixels and a height of 432 pixels. I just picked a couple random numbers. And when we do that, it opens this little window. Oh, does Windows 11 not have shake anymore? I can't close the other stuff. It opens this little window we can draw on. Got our minimize and our close. And gives us a drawing surface to add to our program. And then we can draw stuff. And this is why I've mentioned the mode, is before long, our flowcharts are going to get pretty long. The pictures are going to get big. So we can clean those up a little. Notice that there's tabs up here. So we have this main tab. If we right click on that, there's 2 things we can add: a subchart or a procedure. A procedure is a separate piece of code. We're going to talk about that in a couple weeks. That's where that's a completely separate thing. But a subchart, that's kind of like we just took part of our flow chart and drew it somewhere else. So that's a good thing to help organize the code, is the subcharts. So you can right click on the tab and do that, or you can bring in a call statement. Oh, I have to save. Fix. And if you ask for something that doesn't exist yet, it's going to try to create a subchart by default. So say we'll call, I'll call it math plotting. This first one I had in, yeah, and then if it doesn't know what that is, it's going to ask if you want to create a new subchart with that name. You see, now we have a new subchart with the start and end of a flowchart, so we can do stuff. And then as we're running through our flow, it starts, it gets down to this one. Then what that does is it jumps over to this other plot here, runs through this, and then comes back to our main plot and continues on down. Yeah, do you have a question, Tyler?
Is that what invocation is?
Yes.
Okay.
Yes. That's it's using, that's an example of invocation.
Okay.
As we talk about through the semester, it's we're going to invoke something that's not immediately at hand. So like open graph window is pre-built.
Okay.
Or the next thing we're going to do is going to be messy, so we're going to move it somewhere else to organize it, and then we'll just invoke it from our main.
Okay. Cool. Thank you.
Oh, whoops. So I have to erase all this ink. Oh yeah, and notice there is a tool here, a little pen tool that can be very helpful if you're trying to debug a program. If it's not working right, start making notes right there on it. Write down what numbers are at each step and stuff, and then compare it to the watch window and make sure it's doing the right thing. So this first one, I was just going to relate back to math class, so that you don't necessarily need to follow this, but a quick first example on this, and then we'll get to the one. I guess it is still a good one to follow. So pretty much everything for the graph window is invoking, because, well, Raptor was originally created by the Air Force to teach new programmers stuff, which, by the way, that's why there's so many backups. The Air Force started creating this in the mid-90s, and well, throughout the 1990s is when they were working on it. And back then we didn't necessarily trust our computers to keep running consistently. We expected computers to crash a lot more than we expect it nowadays. So Raptor is constantly making backups. You can delete those backups. That's just a remnant from when computers would constantly crash on us. But it was designed to help new programmers learn to program. So complicated things like working with graphics are all pre-built things that we will invoke as needed. So for math class, we have our X and Y axes and then plot points, right? So in Raptor, I just mentioned the X and Y standards, Y goes down, but they also turn that around to match math class. So when we draw in Raptor, X goes to the right, gets positive to the right and negative to the left. And Y gets bigger as we move up and smaller as we move down, like the ones you're familiar with from math class. So that's one I always like to start off with here. I'll make an offset of like 10 pixels, because 0, 0 would be right in the corner. So if I want to draw the axes, it'd be right at the edge and we wouldn't hardly see it. So I'm just going to offset it by like 10 pixels over and 10 pixels up, and then draw a couple lines, which is just that instruction. If I start typing draw, you'll see the options we have there. Draw arc, draw bitmap, draw box. Usually when we're programming, the computer knows all the keywords it's expecting to see. So we'll get predictive text lists like this. And depending on the situation, those can get very dynamic and advanced, what is being predicted. And making typos is a human trait, not a computer trait. Computers will never make typos, right? So let the computer do the typing as much as you can. So I'm gonna start with a math class thing. So first thing I'm gonna do is draw some lines, like to represent our axes. And I'm gonna put something on the board real quick while we're talking about this. While we're talking about this, I'm gonna erase this side of the picture. Hopefully this is okay. Everybody got that in their notes. Everybody that was taking notes got that.
It's been up there for a moment. I like to ask, but
Yeah, we'd already moved on to something different. So you might remember from your math class, when we plot things to represent values, we use to represent a plane, a flat surface, we set up some X coordinates going horizontally and Y coordinates going vertically. So that's essentially the drawing surface we have in Raptor. And if we wanted a point, like become 1 over and 2 up, we give those as pairs, an X coordinate, then a Y coordinate. So if we want to do more than just a point, there's a couple things we might need. For example, a line, we would need 2 points. I'll say X1, Y1, and X2, Y2. So if we tell the computer there's those 2 points, it can very quickly find them. There's also the points on the screen relate to pixels. That helps us determine where we're placed at and stuff. So the computer can find those and draw a line connecting them, just simple connect the dots. A circle, that's almost the definition of a circle, or exactly the definition of a circle is all the points equidistant from a central focus. So we have our central point, so we have an XY point, and then some radius, and then the circle is everything that's that radius away from the center. So to draw a line, we just need those 2 points. To draw a circle, we need 3 numbers, our X point, our Y point, and the radius. Then obviously some other information once we get to the screen, like what color is it? We're going to fill in the circle or leave it empty. Other things we can put in, but we just need 3 points to represent that. A rectangle, we can do with 2 points. So we have X1, Y1, and an opposite corner. That was awful close to the other one. X2, Y2. Then the difference between those 2 X points tells us how wide our rectangle is. Doesn't matter if they're top or bottom coordinate, as long as they're opposite corners. The difference between those X's tell us how wide it is, and the difference between those Y's tell us how tall it is. So we need 4 numbers or 2 points to define a rectangle. And then other information like what color is it? We're going to fill it in. Do we want to put a picture there so that it looks better than just a solid color? That sort of stuff we're going to look at here. We'll be looking at here for the next few minutes. That's our basic starting point. We also have arcs, which would be part way around a circle. We don't have to go all the way around the circle. And our other main one, I'll do with a triangle, is most of our other shapes, we just do as a polygon. As we get more and more corners, it's going to look smoother and smoother, right? That's another definition of a circle, is it's a polygon with an infinite number of sides. There's all points. It's all points and no lines connecting the points. So a polygon with an infinite number of sides is a circle, but anything between 3 and infinity, we can just make a list of points and then the computer can just connect those dots and make a shape. So for a triangle, we'd have X1, Y1, X2, Y2, X3, Y3. So for a triangle, 6 points. We could do a square that same way, but jumping ahead to a hexagon, 6-sided shape. If we wanted a 6-sided shape, a 6-sided shape has 1, 2, 3, 4, 5, 6 corners. So we would need 6 points, so 12 numbers to draw that shape. And that's kind of how we're drawing on the screen. So I'm gonna start with just some lines like we would do in math class, lines and a point, but I'm gonna draw a circle because a point would be 1 pixel, which is kind of hard to see. So over here, we'll set an offset so we can draw our axes a little bit off of the edge so we'll see them. So the instruction we want is gonna be draw a line. And like I was saying, it's a good idea to let the computer do that. And that's what it's just putting on the board. We need 2 points to draw a line. So I'm gonna start at 0. So all the way at the left-hand edge. And I think I made it 765 wide. So go straight across. And then for the oh, wait, that's not what I wanted. That should be a Y one, sorry. So start at 0, but I want to lift it up a little. So that's why I put that offset. Because I want to offset 10 pixels up and 10 pixels over and make that the new 0, 0 to plot with. And then I'll go 765 pixels over and all the way up to 0. Oh, one of those is a little off. And well, that's going to be the axis on the line, so I'll make it blue. Oh no, this is still offset. So both Y, sorry, I got distracted. Use this pen. Both Y coordinates are the same, but our X coordinates different. So we'll just go horizontally. And over on this side will be this many units up. And when we get over to this side, we're still this many units up. So just a straight horizontal line across. And that talking it through and thinking that might be helpful. And that gives us a blue line going straight across. Oh, 10 pixels looks awful close to the bottom. So I'm gonna check that again. Let's try 30 pixels for that offset. Looks a little bit better. It's raised up a little bit. And we don't necessarily have to go all the way. So maybe instead of 0 to 765, go from 10 to 755.
I have a quick question if that's okay.
Yeah.
So if you're setting it to offset 30, why do you, because you're plotting those points like you would normally on a graph, right?
Yes.
Okay, so why wouldn't you just put the point on where you want the point to go instead of setting an offset and then typing out offset? That just seems like you're adding an extra step.
So that's for consistency. So I wanted to do sort of like a math class plotting.
Okay.
And if we use 0, 0, that's way down here in this corner. So our axes would be like right here at the edge.
Okay.
Or right. And then the vertical axis, which hasn't been drawn yet, would be right at that edge. So the offset just moves it like over here.
Yeah.
So then when we do some math and plot a point, we can adjust that by offset so that right here becomes the new 0, 0.
So if that's when you offset in the first assignment, why do you have to put that when you're putting in the plots? Because if it's already set in the like program as it's offset, if it's like a preset assignment, why do you have to restate it instead of just plotting how that would be at the normal axis or whatever?
Oh, okay. So yes, the computer does not know that. So that gets into that thing where we take it for granted. So when I said that we're going to offset our stuff by 30 pixels, you know exactly what I meant, right?
Yeah,
But the computer does not.
okay,
The computer has no idea what the word offset means. I made up that word just to help organize it myself.
okay, I got you.
That's a
Thank you.
variable, and we'll talk about the naming. So that is just for consistency, because alternatively, we could have typed 30 here and 30 here. Or actually, the first time we typed 10, right? So we could have typed 10 here, 10 here, and run that check. And it was like, oh, well, after that first check, I was thinking, well, that's not quite enough. Then we'd have to come back and rewrite 30 here. It's really hard to draw with this pen. And write 30 here. And every place else we'd have to use that, we'd have to rewrite it.
Okay, I got you. Thank
But
you.
having it saved, all we need is that word. So all we have to do is come back and change it in one place. And every spot we wrote that word gets updated automatically.
Okay, I got you. Thank you so much.
You are welcome. That is one of our main topics for module 2 is variables and why we do that very thing. The first thing to look at is yes, so a question popped up in the chat room. If you have 2 different offsets, would it be angled? Yes. So that's like saying, instead of offset here, if I wrote, well, that was 30 pixels. So instead of 30, I'll write 78 pixels. Whoops, need a comma. I'll write 78 pixels. Then when it runs, that line goes from 1030 up to I think 755, 78 is what was typed in there now. So yes, I was introducing this so that you can kind of so y'all can kind of start playing around with this, because this is a great way to see the step-by-step and sequence and orders and things and how they matter. So the first thing that comes in most useful for variables with Hannah's question is reusability. We're going to type that number is going to show up a lot. And if we need to change it, it can be a lot. That's a lot of places that we would have to change it. But if we have it stored somewhere and just use that word, then all we have to change is where we initially stored it, and it'll update everywhere else. So that'll work for the first one. Then we can call our horizontal one the same way. Draw a line. I'll just scroll down and hit tab, which the predictive text in Raptor, sometimes tab works, sometimes it doesn't. So I guess give it a try and see if it works or if it doesn't. So this time our offset is on the X, so that offset like brings us over 10, and then we'll draw a straight line going down and still have that same offset, or 30 pixels or whatever our offset is currently set to, or easily adjusted. So if we need to draw something like in math class in the 3rd or 4th quadrant, we can quickly change that offset as far as which quadrant we're looking at, which we're going to come back and do actual plotting. I think in around module 5, when we're doing more complicated programs, we'll actually do some plots of the thing. I just like to show this early because it's one that does, it's a useful way to learn stuff, to actually see the visual representation. So I guess this can start 10 pixels down, and at the bottom, we're still offset however many pixels in the X. And I forgot what the height of our screen was. I think I did 765,432. So 422 to back that off 10 pixels. Oh, and that'll be blue as well. So that gives us like our axes on there. Then we could go through and draw every single little tick mark to space things out, which, if you think about that, you should quickly realize that that's going to be a lot of code, except until we get to the point that all of those tick marks are the same. So We need the computer to write those. We don't want to write all those. We don't want to write the code for all of those tick marks. So that part will have to wait till the computer can write those tick marks for us. That's why the actual plotting the output of our program is going to wait until we see the repetition structures. I guess I'll plot a circle just to get started on this, and then after a break we'll draw a couple more pictures and then talk about some more stuff and then do our other example. But my recommendation for starting out and learning about algorithms is going to be to do stuff like this. So we can also draw a circle. I'll draw a couple circles actually. So draw a circle, and then there's the things we were talking about. We need 3 numbers to define a circle, some central point. So I'm going to come offset plus 37. I just kind of made that number up. So offset, like the XY coordinate offset represents our new 0, 0. Actually, not quite. The bottom minus the offset represents our 0, 0. Oh yeah,
You're just defining a new offset.
So offset is our 0, 0. Sorry, I had to pause and think about that. And that's another thing, and that is not consistent across our programming languages. Some of them 0, 0 is the top left. Here in Raptor, it's the bottom left. Sometimes they went ahead and set 0, 0 as the center, like we would actually have in math class. So you do have to know the language you're in. So for a Y coordinate for offset back to the 0 and then up maybe 76, then how big is our circle? I'll just do 12 pixels for now, and maybe green. And notice all I typed was GR and then hit tab to get it off the list. And filled is true or false, but Raptor allows us to write yes and no. So that will actually be my recommendation for this class if you're just starting out. If you've had some programming before and are used to using the words true and false, you can feel free to do that. But my recommendation is going to be go ahead and go with yes and no, because that's how we say true and false in normal daily English, the language we speak, right? So those words should make more sense as we think about things. So that gives us our axes and then some point plotted. And we'll do this in more detail later. I'm going to draw one more circle on here. So I'll select it over here, and this time I'll just click instead of dragging and dropping. So I'll draw another circle, like plotting a second point. And I want this one to be really close. So I'll say offset plus 30, then offset plus, what was the other one? 76. So 80 will work with a radius, then make a radius of say 9. And I'll do a red circle. And yes, fill it in. And the reason I wanted to draw at least 2 here is to show that they do overlap. So the order things get drawn in. So the first instruction it hits gets drawn further back, and subsequent instructions get drawn right on top of things. So that also makes drawing a great way to practice our sequential tool. So I want to look at a couple more things on drawing, but it's probably about a good time to take a break, right? And then afterwards, I was thinking a stick man. That seems a nice little thing. A stick man with like a green box for the ground and a white circle for the sky, and just do a simple picture because I feel that is a great way to get used to focusing on this process, because this is the biggest one that humans just take for granted, is focusing on that order. That's our instincts, right? When we look at something that needs done, our instincts tell us what order to do those things in. So when we're learning to feed instructions into a machine, that's one of the first things we want to focus about. And that's the thing about this course. I like to summarize it as feeding instructions into machines. That's something everybody going into IT is going to need to know how to do, not just the software developers. That's why I lean more towards the Flowchart stuff than the Python stuff during the course. But we will still see some of the Python stuff. But first thing, we're going to draw a little picture, a stick man standing by a house or something, couple with rectangles and circles, maybe a triangle or two. Simple picture, but it's probably a good time to take a break, right? I know I'm getting really thirsty after an hour of talking. Does 10 minutes sound good to everybody? Or anybody?
good.
All right, so 2:13, we will get back to it at 2:23. So I'll see y'all in just a moment.